Okay, so welcome everyone to this session on gas economics. Very important session. We're going to have 4 presentations today, and for each presentation we have 20 minutes for the presentation. I'll be here controlling this time, so I will let you know 5 minutes before that your time is about to expire. So then you try to go to the final message of your presentation, okay? And then we're gonna have some Q&A, and then we're gonna move to the next papers. So who is the first one? Because I don't have the program. Okay.
It's me.
All right. So
Behrang.
You can start your presentation on designing a highly renewable decarbonized energy system, the sector decoupling effect. So welcome and have a good presentation.
Thank you. Hello, everyone. Just to make sure, do you have my screen?
Yes.
Oh, yes, yes.
Great. So I'm starting. So greetings, everyone from Paris. I'm Behrang Shirizadeh. I used to be a PhD candidate in CIRED, and this work is actually a chapter of my PhD thesis, but now I work at Deloitte Economic Advisory. Here we do research as well. So that's why I have these 2 different titles. And I stay as an associate researcher for CIRED as well in France. So here I'm going to present a very recent work of mine, basically an updated version of a previous work of mine, which is a revision, which is called Relative Role of Electricity and Gas in a Carbon Neutral Future. And this is based on insights coming from an energy system optimization model. And of course, it's for France for 2050 to see how we can reach to carbon neutrality in France by 2050. So to jump to the context, we know that according to European climate law, all the member states of Europe altogether should reach to climate neutrality by 2050. And France also had this recent energy climate law, now not so recent now, but in 2019, that France is also engaged to reach climate neutrality, so zero greenhouse gas emissions by 2050. However, today it's really quite different than what we're expecting for the future, because primary energy mix of France has a lot of fossil fuels, nearly half of them. And of course, we consider nuclear without its losses of conversion to electricity. So it's actually much more. And we can see that the share of renewables is very minor. The share of biogas is nearly nothing here today. But the role of renewable gas in different French energy transition scenarios, as you can see, SMBC2 is French Ministry of Ecological Transition and Solidarity's official plan of the country, which is 20% by 2050. Negawatt is an association, a French association, which also considers projects 20%, and ADEME, a French half public energy and environment agency, which also predicts 16%. However, we are quite far from it. As you can see, in biogas, we are less than 0.5%. But all these scenarios, they are quite interesting and nice, but they are all top-down allocation of energy sources and carriers. So there is no optimization. However, we believe that a rigorous energy policy should be based on optimization, where we should include the main energy sectors, and it should be based on endogenous carrier and technology choice. And also it should include most of the low carbon options. I mean, not all, but at least some representative ones. And it should have at least an hourly temporal resolution to take into account the variability of renewable technologies. And also we should be able to internalize these positive and negative emissions by some social cost of carbon introduction. Well, when we look at the existing literature on the optimization, we see that it's mainly on the electricity sector. However, recently we had some sector coupling literature, basically coupling different sectors and allowing an endogenous interaction between them by optimizing the whole system. This is called sector coupling. And this is the most optimal case for a full system. However, these existing studies that are quite recent are either suffering from lack of temporal precision, or a lot of sectors are chosen by top-down allocation, so exogenously, such as these recent works of Tom Brown, for example, that is very concentrated on electricity and electrification. And also in none of these studies, their emissions are internalized correctly, at least direct. I mean, I'm going to talk only about direct emissions, but even direct emissions are not really internalized because we don't have any payment for negative emissions and we don't have any costs for positive emissions, but it's mostly based on some emission capping mechanisms and shadow price for carbon dioxide. So what we asked as questions is like, what is the relative role of different energy sources and also renewables, fossil sources with CCS or without carbon capture and storage and nuclear power? And also, what about the different energy carriers? And of course, importance of social cost of carbon, which is basically the value that the society attributes to one extra ton of emissions of carbon dioxide, which is presented like carbon tax or euro per ton CO2, but carbon tax is only a positive emission value. However, social cost of carbon can be also negative and it can give some remuneration. So to do so, I developed an energy system optimization model. So let's take a look at this simplified version first. We have this electricity network, as you can see, with its own production technologies in round, and also its storage options, and a load, which is in triangle, electric load. But we can, first of all, we can decompose this load to have specific electricity load and transport sector, and also heat load for electricity, heating from electricity, and also hydrogen if we are to replace coal in the industry by hydrogen. And we can also then take into account the gas network with its own supply options, mainly its natural gas and renewable gas technologies, so methanization or pyrogasification of biomass, and with its storage, which is already existing. So we can also satisfy the transport and heat demands partially by gas network. And also we can produce electricity from gas by thermal plants with or without carbon capture and storage. And also we can do some power to gas by methanation from electricity to gas. On top of that, we can also take into account the heat network, which can satisfy a part of heat demand, which should be low temperature heat demand, and it should be a dense area. So basically the big cities, or at least cities, with, of course, its own storage options. So also we can consider a carbon dioxide network as well, because we are supposed to maybe capture some carbon dioxide to store it. And also we can do methanation by using biogenic carbon dioxide, which is a byproduct of methanization, so anaerobic digestion. So then we will need also to have to account for the network for carbon dioxide. So it becomes something like that. There are a lot of technologies. I'm not going to enter to them, but supply technologies are less. What I consider here are four main energy vectors: electricity, gas, heat, and hydrogen, because we are probably not going to have coal by 2050, at least officially, we are not expecting it as energy source. Of course, we may have it as primary material, but not as energy source. And also, I consider all the main energy sectors, so buildings, residential and tertiary, agriculture, industry, and transport. And the main end users: mobility, heating, electricity, so this is specific electricity, and hydrogen for the industry. Of course, heating is classified in three groups: low temperature, which can be every technology; mid temperature, which is some of electrical technologies and combustion of gas; and high temperature, so more than 300 degrees, it's mainly in industry. And although we can produce high temperature heat from electricity, but it requires a lot of structural changes. So I consider exogenously that it can only produce from gas and combustion, so renewable or natural gas. So I applied to continental France this model for the time where the horizon that I consider is 2050. So all energy demand, cost, technical and availability constraints and potentials, everything are 2050 forecasts. But we don't have weather data for 2050, at least not publicly available in hourly resolution. So I consider 2006 as a representative weather year based on a previous work that I modeled 19 years, and I saw that like we had concluded that 2006 is a representative year for the from 2000 to 2018 for France, and it's kind of half climate cycle. So it is reliable, let's say. That's what we consider. So, and this is of course a greenfield optimization model. So it's only a static model, and I'm just gonna show you a 2050, an ideal 2050, where we are constructing it from nothing. And if we do some optimal investments based on all these hypotheses that I counted. So let's take a look at the primary energy production. This graph shows the yearly energy production from each of the technologies as a function of social cost of carbon dioxide. So I made a variation from 0, no carbon, social cost of carbon, to 500. The colors are representing the different technologies. So this brown color is natural gas. The dark green is methanization, so adiabatic digestion. So this is a renewable gas, and pyrogasification of biomass is the light green. So it's also renewable gas, but it's coming from, it's produced from biomass. So it's produced from solid renewable sources. And this pink color is nuclear energy. Light blue is hydroelectricity. Yellow is solar power and solar electricity. And steel blue is onshore wind power. And the normal blue or sky blue is the offshore, ground mounted offshore wind power, not floating, but grounded. So here, as you can see, well, let me just clarify one point. All these gas production technologies are represented in terawatt-hour, thermal terawatt-hour, so their useful form. And all the electricity production technologies, so nuclear and the renewables, they are all presented in terawatt-hour electric, so they're useful primary energy source. If we take a look at this, we can see that without any social cost of carbon dioxide, more than 70% of primary energy comes from natural gas. However, as we increase the social cost of carbon dioxide, so I will call it SCC to make it faster, it reduces, and we can see that for 200 euros per ton of CO2, we have no natural gas in the system. So basically there is no fossil. And this is natural gas phase out. On top of that, we can say that although the energy system seems quite highly electrified, as you can see up to this pink color, mostly it's electricity, but still we have at least 20% of gas in the mainly renewable now, once it's carbon neutral. We have at least 20% of gas in as an energy source, energy vector. And nuclear power, as we can see, it appears for 100 euro per ton of CO2. So this is the pink color, and it never exceeds 8%. And it also disappears in high social cost of carbon dioxide. So I'm not going to enter to details of it, but it's because of the fact that we do a lot of methanation when we have a lot of high social cost of carbon dioxide to burn this methane to produce electricity with carbon capture and storage to make money from negative emissions. That's the reason, in fact, but I'm not going to enter detail because I'm going to lose a lot of time on it. But you can ask questions if you want any clarification. So if you take a look at this, each energy carrier, for example, electricity, this graph shows the electricity production from different technologies. And the negative part is the use of electricity in different sectors other than specific electricity demand. I'm not really going to enter into the details because the main messages were already in the primary energy supply side. I'm going to mostly go to transport and heating sector. But before that, I also want to show you the gas supply and also, again, in the negative side, the use of gas in different sectors. So this purple color is the mobility. The red color is gas or electricity in both of the graphs to heat. And as we can see, in the beginning, we have a lot of gas, which is because a lot of other sectors are gasified, highly gasified. However, as we increase social cost of carbon, we increase the electricity production and its consumption in other sectors, and we decrease gas production and its consumption in other sectors. But still, without entering to details, let's go to take a look at transport and heating sectors. This graph shows the annual transport demand in billion kilometer vehicle. So this blue color is electric train. So it's just the train which is fixed exogenously because we already have electric trains. And this light green is electric vehicle for light transport. And then we don't see it, but there's very little tiny bit of electric bus on top of that, but it's really nothing. And then we have dark green, we can see a bit of it. It's electric vehicle for heavy transport. And then we go to reddish colors, which are internal combustion engines based on gas. So I have only gas and electricity as vectors, but we can also consider gas as a representative for liquid fuels as well. We can see that without any social cost of carbon dioxide, most of the transport is gasified. Actually, even light transport is nearly completely on gas. But by increasing the social cost of carbon dioxide, even for €100 per ton of CO2, we have already nearly all of the light transport is from electric vehicles. And then, but still, as you can see, the heavy and bus transport sectors are still remaining gas fueled, even for high carbon tax, although we have a small part of electricity in them. And so if we take a look at so basically we have a highly electrified transport sector, but not for all the types. And of course, I don't consider boats and airplanes, which can be different. I'm just considering internal transportation of France with no airplane nor both. So if we take a look at this second graph, this is heat demand and also production by sort, again, as a function of social cost of carbon dioxide. Again, here we can see that for zero social cost of carbon dioxide, it's more, we have around 80% of heat production from gas. However, as we increase the social cost of carbon dioxide, this light green, which is resistive heating, this red color, which is centralized heat pumps, and this orange, which is individual heat pumps, are taking over, and it becomes like half electric and half gas. And again, as we increase it from 200 on, most of the heat is electrified. And this small part, which is remaining still in dark green, which is individual boilers, this is because of the industry. So high temperature heat demand that I already fixed it, that can be only satisfied by gas. So now let's take a look at the emissions of such a system. So again, this is the emissions of the energy system, direct emissions, of course. I'm not considering indirect emissions as function of social cost of carbon dioxide. As we can see, for zero, we have high emissions, like more than 150, nearly 200 actually, megaton of CO2 emissions. But as we increase the social cost of carbon dioxide, we decrease obviously, and we reach to carbon neutrality and €200 per ton of SCC value. And as we increase it, we can go up to minus 25 megaton of negative emissions. And
Behrang,
if we take it, yes?
You have 5 minutes, okay? 5 minutes
Great,
left.
thanks. And if you take a look at the cost, so here I have to make a small definition. In my objective function in the optimization, I have the social cost of carbon dioxide, which is internalized. So we have basically a technical cost part, and on top of that, we have this virtual social cost of carbon dioxide, which is not virtual, but it's an internalization of an externality. So this field line shows this social cost, including the social cost of carbon dioxide. But this dashed line is only the technical cost. It is only the material and physical cost of the equipment and energy technologies. What we can see here is that, so basically this difference between these two is actually the value of emissions, so the cost of carbon dioxide emissions. So when the technical cost is below the social cost, it means that we have positive emissions. And when it's on top of, it's above the social cost, so this dashed line is above the field line, this is the other way around. So we have negative emissions. We can easily see that this divergence, so we increase the negative emissions from €400 per ton of CO2 on, and that's where we have also a big convergence between these two costs, which can go up to nearly 12 billion euros per year. So it's basically 15% of the technical cost. So it's a huge value, and this should be also discussed and studied where this money should come from, because it's negative emissions, so people are only remunerated for it, but where this money comes from, this is also an open subject to study later. So up to now, we had only the case that all the technologies were available, but I also studied several case studies where some of these key technologies, key low carbon technologies, are not available. I constructed 4 alternative scenarios of availability of technologies without carbon capture and storage, without nuclear power, without renewable gas, and without renewable electricity. So this graph shows the cost of each case as a function of social cost of carbon dioxide. As you can see, the purple color is without renewable electricity technologies, variable renewable, so wind and solar technologies. Blue color is with no renewable gas. and green is with no nuclear, EPR, so it's European pressurized water reactors. That's because we consider only the new nuclear power plants. And CCS, no CCS is without carbon capture and storage. And the red color, which is not visible because it's behind this red, is this green line, is the case that I actually presented right now. So all the technologies were available. So what we can see, if we take a look at this graph, we can see that this purple line is the one in the most above, in the highest part, which means that without renewable electricity sources, we have some economic inefficiencies. So renewables are useful, renewable electricity technologies are useful from an economic point of view in the cost optimality, actually, for low social cost of carbon dioxide. As you can see, it's in the left side. And when we look at the right side, it's the blue line, which does it. So what we can conclude here is that variable renewable electricity technologies and renewable gas are the main enablers of cost optimality in the energy system in a carbon neutral future. And if you take a look at the emissions, this graph, the colors are representing the same scenarios. This one is the annual CO2 emissions as a function of social cost of carbon dioxide. And as we can see, it's again the same message, renewable electricity and renewable gas. However, this green color shows the nuclear power, which is actually stick to the red one. So in both of the cases. So nuclear energy has very limited and small environmental and economic benefits in a carbon neutral future. So that's all. I'm just leaving my conclusion here because I think I'm out of time. So you can just read and ask me any questions that you have. Thank you for your attention.
Thank you, Behrang. Very interesting presentation. Congratulations. It's very clear that the price of the carbon will be key to the decarbonation process. I would like to know if any of the colleagues have questions for Behrang.
Yes, hello, Behrang. Thanks for this interesting presentation. I would have some questions. It's two questions basically. So you considered France as an isolated system, but obviously France is not isolated. What could be the impacts of the neighboring countries on the system? Is there anything that you could say on this?
Yes, sure. I think you know better than me, but basically when we have a highly renewable system, the interconnections are actually helping to manage this variability. And so as we see, the optimal case is like more than 90% renewable and even 100% for some social cost of carbon values. So it means that actually having the interconnection with neighboring countries will help us to have this geographical aggregation and probably reduce the required storage tech. So I didn't present, but we have also heat, electricity, gas storage technologies, batteries, pumped hydro storage, and even, well, now power to gas is just a conversion technology, but for heat also we have either central or decentralized heat tanks. So we will basically just reduce the required storage technologies and it will probably cost less. But one point that I want to highlight here is the fact that it's a greenfield optimization model and with copper plate assumption. So it's one single node. What it means that I don't take into account the required increase of the cost of transport network. It can be more, but there are some studies that are showing that already the French transmission network operator, for example, that it's of a secondary importance compared to energy production costs.
I see. Thank you. Another question, if there are no others. Okay, that's more technical. So you said that it's important to model renewable energies in an hourly granularity. So from your model, I saw that there's a lot of different technologies, and so I guess this is already computationally expensive. So what is the temporal granularity that you considered in the modeling?
It's an hourly temporal resolution for one full year. 8,700
one full year.
Yeah,
okay.
Yeah, with no representative period. It's continuous year, so it takes like a week to solve it.
Oh, I see. Okay.
And with a lot of simplifying assumptions that, for example, I don't have biofuels. If I had it, it would be much more complicated. So I chose some representative way of showing all these fuel and gas together.
I see. Thank you very much for your answers.
Thank you.
Any other questions for Behrang?
Actually, I'm very curious about you were talking about nuclear on slide 6 about the negative. It was negative costs, right? Can you please explain about that, because it's actually very interesting.
This here, right? When we don't have nuclear in 500 euro per ton of SCC. Well, the point is that nuclear power can be very useful to produce extra electricity because it has a small and dense electricity production, which renewables don't have it. But there is another problem here, is the fact that if we nuclear power has also its variable costs, both in operational side and also in fuel and waste management and all these points. So, however, renewables, they have zero marginal cost. So if we over-dimension the renewable electricity production side and we produce more renewable electricity, we can do power to gas for free when it's more, when we don't need it. Because there are, in a fully renewable power system, in a previous study, I found that around 20%, even more, 25% of the time, the electricity price is zero. So it's exactly that. So if we do methanation for power to gas, we produce gas from this renewable electricity, where nuclear is going to be a bit more expensive. It's going to be maybe 15, 20 euros per megawatt hour. So it's not an expensive price, but still compared to renewables, it is more expensive from this market point of view. And that's the reason why we do a lot of gas, but we don't need to consume that much gas. So we do also a lot of gas to power with carbon capture and storage to make negative emissions and make money from that. Actually, in another previous work again, in energy economics, I had also analyzed this business case for negative emission technologies. So I had natural gas with CCS, so it's residual emissions, and biogas with CCS, which is negative emissions. And also methanation with CCS, so it's electricity power to gas with CCS. It was very clear that power to gas had no interest to enter to the optimal solution, except the fact that it had a lot of income from negative emissions. So their main incentive to make methanation with carbon capture and storage later is just to earn money from the emission side, but not really from electricity market. And this is exactly what happens here, I believe.
Okay. But a point that can be made is that to produce the same power as a nuclear facility, you might need a very, very, very large terrain to insert your variable renewable energy sources or your methanation
as you're right, actually from 300 euros on, my onshore wind power, which is still blue here, is capped. So it's and offshore is increasing, as you can see by that's because we have I used very pessimist limits about this future potential of renewables, which are like the minimum that we found in the literature for France, and they are mostly capped. And
so
as you can see,
you take that into account.
Excuse me?
You take the space constraint into account.
That's of course I took it.
Okay.
I have a limit, but of course still it's a big surface, but it's a limit. I have a limit and it's already capped.
Okay, thank you.
You're welcome.
Behrang, just one question. Maybe I missed some methodological question. Why, when the social cost of carbon is zero, you don't have liquids here?
Actually, I was just saying, it's a very time-consuming and complicated, long modeling. So I considered all the fossil sources as just gas. I don't have any liquids. But I mean, if liquids are cheaper than gas, they will take a part of the gas, a part of this. Otherwise, it will be gas. So it doesn't really change the main conclusions. That's why I made this choice. But of course, it would have been better to present also fuels, biofuels, or every other possibilities, but I didn't.
Thank you. So
Thank you.
I think that maybe we are running out of time and we should move to not have problem with time with the other presentation. So now we're gonna move to the presentation of Sebastian. on obsolescence of the gas distribution grid in urban areas, an open source modeling approach for the gas phase out in local neighborhoods. Okay, so you have 20 minutes, Sebastian, to make your presentation. Have a good presentation.
Thank you very much for the introduction. Can you see my screen and the slides in the presentation mode?
Yes.
Fine, super. Okay. So hello and good afternoon from at least Central European time zone. Thank you very much for the interesting presentation so far. I really much appreciate to present now one of our latest research topics, which is entitled, now a little modification of the title, Demystifying Natural Gas Distribution Grid Decommissioning. In this work, we investigate a local natural gas phase out in the low temperature heat supply of an urban neighborhood in Vienna, Austria. So today's agenda is as follows. I will start with a very short motivation and background of this work. Then I will continue with the core objective and the novelties, explain a little bit or just a very basic idea of the methodology and the open source modeling approach. Then I will present the results and conclude this presentation with the conclusions and some outlooks. So the motivation of this work originates from the observation of limited expectations for green gas in the residential and commercial heat supply, especially in the low temperature heat supply, where only relatively low. So the following aspects focus in particular on the Austrian case. However, I would say that similar shares and relations can also be observed to other European countries as well. So not only from our perspective, the gradual or complete substitution of fossil gas by green gas is a myopic approach, simply as a result of the numbers. So here you can see some typical numbers for forecasts or projections for the Austrian case. Simply, as the first point is the gradual and complete substitution of fossil gas as a myopic approach. So the second point is that we see difficulties that the quantities of green gas needed for all energy services will be economically available. So we expect an increase of the demand in case of profitable hydrogen or green gas production in different sectors. For example, especially in particular in the heavy industry, freight transportation and mobility sector. And we also see further niche applications of hydrogen and green gas as a result of sector coupling and high efficient sector coupling technologies and specific industry processes. So green gas, we see limited expectations for green gas in low temperature heat supply. So the scope of this work is first, the demystifying the unique or current dominant position of natural gas in the provision of heat services, especially in particular low temperature heat services, decommissioning of the existing gas distribution grid infrastructure, and also trigger emerging sustainable and high efficient energy supply alternatives. So these are the benefits, and we also want to show that no continued repowering of conventional energy technologies are a future business case, no maintenance of known business models. And we also want, as also in the presentation so far, we want to include, internalize the costs of inactions, for example, in this work as penalties for failing to meet climate targets. So just before we jump into the methodology, here you can see some practical European examples of gasless neighborhoods. In particular, the two cities, Zurich in Switzerland and also Utrecht in the Netherlands, can be seen in this respect as a role model. In both cities, at least districts or some parts of districts phase out from natural gas in the low temperature heat supply. And it is remarkable, as the Netherlands are one of those European countries with high natural gas reserves within the country. So in particular, the picture at the bottom is taken in Zurich and shows, let's say, the practical implementation or implications of distribution grid decommissioning on a local level. So here you can see some example of, or some realization of the gas distribution grid decommissioning in Zurich, where you see the practical realization timeline. For example, point number 1 is the cancellation of the gas connection and gas supply. Number 2 is, for example, to submit the application for remaining value compensation. And number 3 is remove the end user's device. So here you can see actually the practical realization timeline, starting at the cancellation of the gas supply contract. And number 5 is in the end, the decommissioning of the grid infrastructure. And also a very important aspect in this regard is the remaining value compensation payments. For example, here you can see if you have invested into an end user's device for a gas supply, gas-based heat supply, for example, in the year 2009, you get in the end a compensation payment of about 40% of the investment costs as a value compensation payment at the end user's level. So this is in the end some very important aspect if we talk about distribution grid decommissioning on the end user's level. We also have to talk about the compensation payments at the end user's level. And this is implemented, for example, in a European country, in the Switzerland, in Zurich. So let's return to the core objective and novelties of this work. So first of all, as I said, the decommissioning of the natural gas distribution grid and corresponding natural gas phase out in the heat supply, low temperature heat supply of an urban neighborhood, to show alternative distribution grid capacities, or to quantify alternative distribution grid capacities, and sector coupling, high efficient sector coupling technologies that are required to ensure an adequate but sustainable development in the provision of local heat energy services. We analyzed in this work in particular 2 different deep decarbonization pathways on a local level. On the one hand, a high electrification scenario where we replace natural gas in the end by electrification of the energy services. And on the other hand, a scenario which is called a network scenario, where we analyze an expansion of the district heating and network all over the district. We introduced in the end to quantify our results by wide range benefit indicators that address both qualitatively and quantitatively the results. And we also, this is to some extent very important, also if we talk about heat supply or energy services on a local level, we also considered the increasingly important cooling demand service needs on a local level. So let's jump into the description of the methodology applied. It builds upon basically and is an extension of one of our work recently published in Applied Energy. In this work, we focused on the energy sharing amount for different consumers within an urban district in Vienna. And we considered high shares of local renewable energy generation. And as one key finding in the sensitivity analysis, we analyzed different CO2 prices triggering a substitution of natural gas-based heat supply by other sustainable alternatives. So if you're interested in this approach, please check out this publication in Applied Energy, and also check out the GitHub repository where you can find the full modeling code and modeling framework open source available, and also further material. So as I said, the model was used in the Applied Energy submission, which is called GUSTO. And this model enables a high temporal resolution of the energy demand. And in this work here, we analyzed the building stock of an energy community, of an urban district. And therefore, we split the existing building stock into different characteristic building types. And here you can see, let's say, some of the inputs for our analysis of the natural gas distribution phase out, where we used the model GUSTO to estimate the increase of the peak demand per building type as you can see on the left-hand side, for a characteristic multi-apartment building. For example, the green line shows the baseline or the current state of supply, the current electricity demand. The orange line shows the case of an electricity-based heat supply, and the blue one shows the electricity-based heat and cooling supply of a specific multi-apartment building within the area. So here you can see in the left-hand side figure that we see an increase of the peak demand per building type, and this was in the end used for a second open source model, which is called Rivos. This open source model is developed by TU Munich and is also available on GitHub. And the information of Gusto's peak load results are used in the open source model Rivos, which bases on graph theory, you can see on the right-hand side figure. It is a mixed integer linear program and enables cost minimizing multiple energy carrier network expansion. Where you can see here in the figure, right, where you can see the sources of a specific energy carrier indicated by the squares and the demand indicated by the triangles. And the model is used to, let's say, optimize the network infrastructure on a specific distribution grid level. So now I want to explain a little bit of the methodology and the extension of the existing model. One of the key findings of our previous work was that consumer connection and network-based energy service provision depends significantly on the distance between the consumers and the existing network. So here you can see the ranges where it's profitable to connect to, for example, the district cooling network, and where depending on the distance between the consumer and the next or the nearest district cooling connection point. So if we have a wide distance to the next connection point, we can only reach low district cooling prices for the energy service in the end. So in this information, the significant dependent on the distance to the network is used in the extension of this work here. So the non-discriminatory right to be connected in the end. We see here is on this sketch the basic idea of this work, that we say, okay, we have this geographic dimension and the distribution of consumers, and each consumer within a district has the right to be connected to the district heating network and is able, let's say, to replace the natural gas in the low temperature heat supply. So you can see here on the left-hand side, buildings that want to be connected to the network, but it's not feasible for them as a result of technical issues and also economical issues as a result of this distance to the next network connection point. So here you can see the extension. We implemented a nonlinear network expansion path, which is a result of the, let's say, basic understanding of network expansions. On the right-hand side, you see a figure where you see the different stages according to the different heat densities of a specific area. For example, you see stage 0 is, for example, the connection of specific consumers in the surrounding area of the existing network. Stage number 1 is an extension of the existing network as a result of high densities, for example, here in this area, stage number 1. And then stage number 2 has lower heat densities, for example, here called mid heat density. So you have to expand the network and only add a small amount of heat supplied. And also in the end, stage number 3, where you have to extend the infrastructure, but only can gain a small amount of heat as a result of heat densities as stage number 3. So this, let's say, nonlinear function between gas-based heat supply as a result of different heat densities and additional district heat line lengths is implemented into the job objective function, where you can see here costs is split into two parts: cost cap for the expansion of the network itself, and also cost economies of scale. Here we called here the second part economies of scale, which is a result of penalty costs for failing to meet climate targets. In the end, it's a result of this nonlinear function between additional district heating line lengths and gas-based heat supply. You can see here, P is, for example, the connection capacity of gas-based heat supply, and this is directly here included into the cost part, which is called economies of scale for failing climate targets. So now 5 minutes left. Fine, 5 minutes left for the results. Yeah, fine. So now let's come to the results. Here you can see, let's say, the fundamental results of this analysis. Where you can see the distribution grid in the district for two energy carriers or two different networks. For example, here electricity on the left-hand side and natural gas on the right-hand side. You also see, as I mentioned before, the different building type categories, where we split the building stock into different categories to, let's say, assume or calculate the projections of increased peak demand. On the right-hand side, you see a massive existing natural gas distribution grid within the district. Here you can see the results of the two different decarbonization pathways. On the left-hand side, as I said, the high electrification scenario, where we replace natural gas replace natural gas and supply the energy services on the basis of electricity on the left-hand side. And on the right-hand side, you see the network scenario, where we replace the gas distribution grid by a massive expansion of the district heating and district cooling network. Yeah, on the left-hand side, you see the specific capacities here illustrated by the violin plot for electricity and district heating. You see the comparison between the current state of supply, which is here called case A, and case B, which is the high electrification scenario. You see the difference in the max line capacity here, and also the difference in the mean line capacity here. And also at the bottom, you see the heat map, where you can see actually the different possible lines that could be implemented to supply the area, and the specific lines that are used in case A, and the additional lines that are used only in case B. And at the bottom, you also see the implemented line for the district heating network. On the right-hand side, similar illustration of the results, so it's nice or easy to compare the results. You see the difference in mean and max line capacities of the district heating network. And also at the bottom, at the right-hand side bottom, you see the matching. If we consider the district heating or the heat service needs and the cooling service needs, we see a high matching between implemented lines for the heating and the cooling network expansion. Only a few lines are unused in the case C in the network example. So here we see, as I said, in one of the motivation examples, it's very important to see the end user level if we talk about the gas distribution grid decommissioning. And here you can see the end user cost parity that is reached between 2043 and 2046 as a result of the internalization of CO2 payments that are as a result of the gas-based heat supply. Here you can see in the end the comparison between case A, which is the current state of supply, and the case C, which is the massive network expansion from the timeline between 2020 and 2050 as a function of different CO2 prices and a specific CO2 price development. And you can see that we have the cost parity on the end user level in the area or in the timeline between 2043 and 2046, which in particular depends on the specific emissions of the district heating network. So if we see that, if we assume the current specific emissions of the district heating generation mix, we reach end user cost parity 2046. But if we assume a halving of district heating specific emissions in 2030, we reach cost parity in 2043. And the yellow area marks, let's say, amount of money that can be shared in solidarity among end users to reduce in the end specific connection costs for a specific end user, which is far away, let's say, from the existing network. So here you can see also qualitatively the two different scenarios. You can see the baseline scenario, which is called case A, and you can see different technologies that could be used to, let's say, feed the energy services, to supply the energy services. You can see in case C, for example, if we analyze, or if we extend the network, we can use green gas, geothermal, waste, and solar thermal to, let's say, feed in as a feed-in technology of the district heating network. If we, let's say, replace natural gas by electrification of energy services, we significantly depend on the end on on-site PV capacities and also heat pumps, which replace natural gas. On the right-hand side, you see the comparison related to CO2 reduction potentials, forex savings in million per dollar, and also, let's say, the comparison of the network on costs, peak load, and the length of the network. So a very last slide, conclusion and outlook. We can summarize that deep decarbonization of local multiple energy carrier systems is possible without being dependent on the existing gas network infrastructure. Possible stranded assets, also at the gas end user level, must not play a decisive role, specifically since the trade-offs analysis in this work show that alternative scenarios of lower zero-emission energy service provisions are even more economical in the longer term, since the CO2 price is expected to increase in the next decades. So the CO2 price is the key determining parameter. And future work should address, among others, in particular, energy generation technologies and the mix feeding into the district heating or district cooling network. As I mentioned qualitatively here, waste incineration and seasonal heat storages. And of course, also include the local mobility service needs into the local energy service needs. So that's all from my side. Thank you very much for your attention and really look forward to the discussion now.
Okay, congratulations, Sebastian. Very, very interesting work. Very good analysis on alternative path to deep decarbonization, and very bad news for the natural gas industry. So I would like to know if anyone wants to put some questions to Sebastian regarding his work. If not, I can start with one, Sebastian. You mentioned the decommissioning of the gas network. You mentioned some examples. Who is paying for that? Is it the utility, gas utility, or is the government? Because apparently at this point it's something very, very expensive. Even though in the long term, with the cost of carbon going up, this would be economical. But in the case that you have studied, who is paying for that, and how do you see this problem of deciding who's going to pay for these stranded costs?
Yeah, absolutely agree. This is an important aspect in this regard. So in the end, the costs have to be shared, solidarity on all users and all participants in the market. So in the end, also at the end user levels, but if I just switch to this slide, so we see in our results that in the end, we see a better economic performance also at the end users level if we have high costs in the KC network scenario where we have this massive expansion of the network. But in the end, as a result of the increasing CO2 price, we have a better profit performance also at the end users level. So the costs have to be shared, solidarity on all participants in the market or in the supply chain. But in the end, we see some benefits also from the profit side.
And another question: when do you think the government should be starting to decommission the network? When they should start as soon as possible, or when the cost of carbon make it more economically sensible?
Yes, of course, the development of the CO2 price is highly uncertain. However, I think that we can expect an increasing CO2 price. So the cost of inaction, as you can see also here, we see this cost parity. So the cost of inaction should be internalized. So governments and heat supply companies should start more or less now. We need this to replace fossil fuels also in the low temperature heat supply.
Okay. Is there any other question for Sebastian? Well, so if not, thank you, Sebastian, for this very interesting work. And
thank you very much.
Okay, so we need to move now to the next presentation from Lauron. Challenges and opportunities of LNG in Brazilian market by the government program New Gas Market. So Lauron, have a good presentation.
Let's go. Thank you. Okay, let's go. Are you seeing my screen, Edmar? Yeah?
Yes.
Okay, let's go. Hello, everyone. My name is Lauron. I'm an electrical engineer and a researcher of the University of São Paulo in Brazil. And I'm also a buyer of energy and natural gas in markets of Brazil, Mexico, and the United States. I'm here to present our work, which evaluates the challenges and the opportunities of LNG, liquefied natural gas, in Brazilian market by government program called New Gas Market. This work was made with the Professor Drielli Peyerl and Professor Edmilson, both from the University of São Paulo. I'm presenting here from the São Paulo, Brazil. Let's go. The objective of this paper is to evaluate the conditions that was created by the new gas market, the government program called the New Gas Market. This program was created by the Brazilian government in 2019. The main focus here we are the objective of the program is to evaluate to a free market in gas natural in Brazil, and it will create. We can see now we are looking to the possibilities and a series of new opportunities that can be created by this new scenario. The main focus of this study is to evaluate the feasibility, the financial feasibility of import LNG from the United States to Brazil as a source of a mix of natural gas in Brazil. And for this, we have to look to legal conditions that give us this possibility. Let's go. Just to give a scenario, here we have the metrics of natural gas in Brazil. And the second graphic, we have the history of the last years, how was supplied in natural gas in this mix. We can see some imports of LNG linked to when the power generation started up in Brazil. It depends of the power hydropower generation. When in Brazil, explain how this works. When Brazil, the main source of electric power in Brazil is supplied by hydropower plants, but of course it depends on the weather. When we have a better period, better years of about weather, the thermal power plants must be operating. This scenario is repeating this year, specifically this year, and the problems happens next year because Brazil is now passing through a great problem, a great crisis about weather conditions, making our reservoirs of the power plants being a low level, creating a great problem to generate energy from electricity from the hydropower plants. To overcome this problem, the national operator of the electric system is starting up the thermal generations that use natural gas, and LNG is a good options for this situation. Here in this first graphic, we can see this blue triangle that represents the demand for the next years that we don't have a scene how to be supplied. So this is an opportunity, of course, for in this scenario of power generation that LNG could be supply this portion. Just to know about the Brazilian structure, Brazilian has 4 terminals of LNG operating at this moment. 3 of them owned by Petrobras, that is a public company, and just 1 is operating by a private company. There is another project that must be operating this year yet. And about our gas pipeline, our structure is along the broad. Just to comparison, Brazil has something like 9.4 thousand kilometers of gas pipeline, whilst just to compare, Argentina has something like 3 times than Brazil, and the United States has 485,000 kilometers. That it represents something that we can see here, 2 sides of the same view, that how can we do in Brazil just with a so limited structure, and in the same time it could be an opportunity to grow to the area, to the companies in this market, to grow and to invest. Here in this graphic below, we can see how is the capacity and the ociousity of the terminals. We can see from the last years the average median of the use of each terminal, and we can see a great, despite in the years that we have problems with hydropower generation, that the terminal was used to supply the thermal plants. Despite of this, these terminals have a great ociocy that can be used without any new investment. So let's go. Just a view about the Brazil natural gas chain. We have all the parts in all the parts of the chain. So in the upstream, the midstream, downstream, we have Petrobras making the operation, making the process. And despite of this, still in the consumers, we have the great consumers in Brazil as a Petrobras companies, like some power plants, some petrochemicals companies. And so until these days, we can see Petrobras dealing and managing all the chain of natural gas. With this new gas market that was created by the government, one of the main points is to eliminate the private monopolies, like that one that I said about Petrobras, and create some possibilities to give attractivity to the market, make the new players enter and operate in this market, make the opportunities, the financial possibilities and attractivity to the new players, giving a more integration with the electrical system, giving more defined and clear rules about the operation of the power plants, the thermal power plants, when have to be put in the system. And one of the main points is to the harmonization of the state and federal regulations that we have at this moment in Brazil. So just to show what it means, here in the first scenario, we have Petrobras, as we said before, dealing all the terminals, all the productions, all the pipeline of transport, the importation from Bolivia, and everything is dealing by Petrobras. With this new scenario, we can see several companies working, and the new agent, like a storage agent, can be starting up in Brazil that we don't have until this moment any one storage agent working here. And for a free market, it is very important. It's necessary to give some conditions to operate in a free market. So what's the challenges will Brazil face in developing a LNG market? So about looking at the regulatory points, the new rules allows sharing the structure and the terminals to different companies use the same terminals. That is, until this moment, is a great problem in Brazil. All the 3 terminals from Petrobras are operating just by Petrobras, as we saw before, these terminals are not using in his own capacity. It can be used and sharing with different companies. About tax, the importation using gas terminal ends up changing hands and becoming an internalized product. Here we have some problems to talk about the tax sharing a terminal. Different companies, it's difficult to separate the product and to be taxing each one. One challenge must be see when we talk about LNG vessels. It represents a large storage capacity, and it must be linked to a great consumer. That is, it can be a problem. We can see a solution as an anchor or as a great company, as a main consumer, and it give the opportunity to us another little companies at second market behind this great company, something like this. Another big problem is the guarantee required for long-term contracts. The traders require financial guarantees, and requires take or pay to a great company, a great contract. That could be a problem for the dimension of Brazilian consumers. And the price offered by international traders. We'll see in the next slide, importing LNG from the United States, it gives us a reference from Henry Hub, quoted by dollars, and it could be sometimes interesting to Brazil, but of course it depends on the references from the dollar from the other markets that could be in some ways, in some moments, a problem to Brazil. And we can see as a conclusion about this new program from the government that is not completed. It is just the beginning. It's just a little evolution about a whole, but it's important. We can see something that could be dealing in the next steps. Like we must have some it's a question. We must have the operator of the gas pipeline system and network, because nowadays it is done by the same company that is Petrobras. When we have different companies operating the system, must be a combination about the process, about the operation each one. Another point is we must have a chamber to register the contracts of commercialization. When we have in the beginning, we don't believe that it's important, but when the market improve, we must have something to control the several contracts each one has and with which parties has with another. When we talk about storage, one point important is the underground storage. But in Brazil, we don't have a clear environmental licensing or rules to license the underground storage. It's a point that must be worked for the next steps. And about the rules to interconnections, to assess the pipeline is not clear. Is not the rules it becomes not clear, so clear to anyone use the gas pipeline that owns to another company. Another great question, a last mile agent. In the case of failure of the supplier of the gas, who will give this guarantee? Who will make this last mile agent? Because we don't have this agent, we don't have these options, we don't have how to deal with this problem nowadays. When Petrobras get out of this operation. Another point is a standardization of the contracts with the distributors to give more facility to access to a company in several parts in different parts of the country could choose his supplier. Another point is, sorry.
Just to let you know that you have 5 minutes left. Okay.
Okay. Thank you. I'm going to the end. Thank you. Another point is about the supervisory agency. The supervisory agency from natural gas in Brazil is not so prepared for if we have a great evolution in the market. It must be improved. And last of all, the need of expansion of natural gas flow routes from the pre-salt offshore, it must be shared between Petrobras and the other exploration companies, and it must be reach all the exploration in the sea. Here, just to pass, I will let for knowledge, but I make a net back price from importing natural gas, LNG from the United States, and we use some prices, regular prices from the market, and not anything special, not anything negotiated by a company for special. But we just want to see that despite nowadays Henry Hub is in a levels not so attractive, despite of this, liquefied natural gas in Brazil is still attractive with prices that represent lower than some what Petrobras sell to the distribution company or to anyone in Brazil. And we can see just for the last years that in these dots, orange dot, we can see the tendency that everyone, the LNG is taking lower prices than other options from the mix we have in Brazil. So just to take the conclusion, there is a favorable trade conditions to import LNG from United States to Brazil. West supply LNG price is around 90 or below $90 per million of BTU, which compared to domestic price represent commercial viability. This reference from Henry Hub prices is seen by a low prices in the future that provide attractive financial conditions to import from Brazil. And of course, the government initiatives with the new gas market enable favorable regulations and conditions to make this importation and operation to Brazil. Just some reference that we are using. I thank everyone, and I'm open to questions.
Thank you, Laura. Very interesting presentation about the gas market situation in Brazil. Lauron has shown that the market is under an important reform process, trying to develop some regulations similar to the ones that we have already in Europe. So if anyone has any question to Lauron, it's a good moment. Lauron, I have a question. Meanwhile, how do you see the competition between the domestic gas and the LNG, imported LNG, in a context where independent producers will be disputing the market, not selling to Petrobras?
Okay. We can see that the domestic gas that in Brazil, we don't see clearly it's so a great opportunity, because there is some problems about the gas from the pre-salt, like there is a great cost to separate the CO2, the carbon dioxide from the gas from pre-salt has a great rate of carbon dioxide, and it make it difficult to process. Another point is the flow, the structure to flow the gas from the platforms to the country, to the country must be improved, must need a great investment from the companies. That until this moment, anyone is considering this investment for the next year. So we believe LNG is a reality, can be used by at this moment for Brazil. And the natural gas from pre-salt is maybe maybe can be used in the future, but we cannot see this future at this moment.
Okay. Is there any other question for Lauron? If not, we have still the next presentation.
Thank you, Edmar.
Yes?
Thank you.
Thank you. Okay, thank you, Lauron. I think it's Liz gonna make the next presentation, right? On the hydrogen opportunities in a low carbon future, an assessment of long-term market potential in the Western United States.
Yes,
Liz.
can you hear me okay?
Yes.
And can you see the presentation?
Yes. So I think we are set to go.
All right, well, this is a very, I think, different starting point from some of the previous presentations. So thank you so much for having us here today. And it's been super interesting to see these, varying perspectives on the evolution of markets under social cost of carbon versus a place like Brazil, where there's actually still, potentially, thriving and enduring LNG market. We're moving to a very different context here with this study, looking at kind of deep decarbonization futures in the Western United States. So just to set things up, so my name is Liz Mettetal. I'm an economist here at E3, which is an energy consulting firm. I'm stepping in for my colleague Anthony, who unfortunately isn't feeling well today. But we worked together on this study in 2024, Mitsubishi, looking at the role of hydrogen in a deep, low carbon future in the West. So the plan for this session would be, I'll give you basically a brief overview of the study that we did. And I'll focus, give you kind of some sense of the methodology that we used, and then focus on some key findings, particularly in the power sector. And I know, I think this work should kind of build on some of the remarks on hydrogen that were at the keynote, and that you probably all have been hearing on the news. I think, the punchline of the study is really around, when and where does hydrogen make sense, and how big is that opportunity? I think, there are probably two things you have to believe that there's a future for hydrogen. One is that you're getting to a deeply decarbonized future. So, at least 90% decarbonization of the entire economy for hydrogen to really fit in along any of the kind of sectoral verticals where you might see it, where it has, where it could be sort of feasibly implemented. And I think the second thing you have to believe is that the costs to produce hydrogen, particularly zero carbon, green or blue hydrogen, need to fall dramatically from where they are today. They will probably never be competitive with the cost of gas, but to be competitive with other alternative approaches to deep decarbonization, whether that's electrification or capture and storage, it's going to be a bit of a race to see which of these technologies can become the cheapest or have such better performance that they are a preferred decarbonization method. So just a quick introduction of who we are. So we are an economic consultancy focused on the energy sector broadly, but really probably most of our work, a lot of our work is on electricity markets in particular. So most of our work is in the United States. We have a handful of studies that we do in Europe and in, we've done a couple of things in India, but most is in the United States and Canada. We are, economists, engineers, mathematicians, policy experts, and, we serve a range of clients, which is, the reason they hire us is because we work for utilities, governments, regulators, environmental groups. And so I think, we have a reputation of being evidence-based and objective in our analysis of energy and electricity markets and the implications of deep decarbonization. And what I wanted to note is that a lot of our studies focus on what happens or how or why we will achieve, high levels of renewable penetration. So achieving targets like net zero or 100% clean energy. And I think, this has enabled us to be well positioned to look at the role of hydrogen, because that's, where hydrogen becomes interesting, is when you start to think about getting that last, 10% of emissions, either whether it's, replacing natural gas in the power sector or heavy duty trucking industry. It's really not until you get to deep decarbonization where hydrogen starts to look attractive. So the objectives of this study were really focused on what is the potential for zero carbon hydrogen. So, estimating potential cost trajectories for low carbon hydrogen in the Western United States, looking at a market outlook for hydrogen and looking at it vis-a-vis other decarbonization strategies where possible. And then looking at the potential for long duration hydrogen storage in a Western power market. And we also did some work on the supply chain, hydrogen supply chain, which I'm not going to focus on today, but all of this is in our report. Our full report is online. And I'll just note that this study really built on probably 100 E3 studies that we've done across the West over the course of the last, decade. And in particular, I think a common finding has been that the development of some form of zero carbon fuel, whether it's biofuels, synthetic fuels, hydrogen, will be necessary to supply these energy end uses that are not easily electrified. I think for a lot of end uses, electrification is emerging as a much cheaper decarbonization strategy, but there are certainly end uses and places where that does not make sense, particularly out, particularly in heavy duty transportation, potentially in industry. And then focusing on the power sector, what we found is that achieving kind of absolute zero electricity sector emissions becomes prohibitively expensive unless you have some form of zero carbon fuel or long duration storage. And so, hydrogen, advanced nuclear, some of these other niche long duration storage technologies or some sort of zero carbon fuel really is valuable in reducing costs of removing that last bit of emissions from the power sector. So typically it's, the cost of switching from natural gas to hydrogen or one of these technologies. So one other point I wanted to know is, why are we talking about a low carbon future? And that's because, a lot of our modeling is not based on comparisons to, say, the social cost of carbon, which I think, super valuable. And it's like a very interesting comparison to do. But we're really, in this modeling exercise, focused on what does the policy say we have to do? And taking that policy assumption as given, and then looking at sort of the cost-effective ways to achieve those policy mandates. So this is just a map of the West and the clean energy targets. So those are targets for the electricity sector are in blue, I believe, and then the gold is the economy-wide emissions targets. And I think, what I'll draw your attention to is, California, for example, wants to have, so they have SB 100, which is a policy that basically says 100% of retail sales needs to be supplied by renewable energy and zero carbon resources, I believe by 2045. And then, they also want to hit carbon neutrality. And then there's several other states in the West, that also have these deep decarbonization targets. And we use that in building some of the price forecasts that inform the modeling for this study. So I'm going to start with a slide just on the production of hydrogen and what we assume about hydrogen production costs. Then I'll talk about some of the analysis that we performed and our key findings. So this is, a spreadsheet model, right, to estimate the cost of hydrogen. Basically, hydrogen can be produced by extraction from water or extraction from fossil fuels. And the cost of hydrogen is going to be extremely relevant to our assessment of its potential applications and how it might compete across different verticals. What we have here is two figures. On the upper left-hand side is estimates of the cost of hydrogen production using proprietary capital cost information from our client, Mitsubishi, who is in the hydrogen market, as many of you are probably aware. And then we also did the analysis using publicly available costs of electrolyzers developed by researchers that we have worked with at the University of California at Irvine. One thing you'll find is that, as the electrolyzer becomes a smaller and smaller portion of the costs of producing hydrogen via electrolysis, that, those differences in the source of electrolyzer capital costs matter a lot less. But so that's like a setup of the two figures. I guess I'll start on the left, and the same thing applies on the right. So what we have here is a huge gold band, and that is essentially showing the range of cost to produce renewable hydrogen. The gold band is from dedicated on-site solar and wind. And there's a green band that's from producing it via electrolysis from curtailed renewables. The purple band is advanced nuclear. And then the two dotted lines, the black one is steam methane reforming, which is, the dominant way of producing hydrogen from a methane source, typically natural gas today. But that obviously has significant CO2 emissions. So the blue band adds on the cost of 90% carbon capture and storage based on costs of CCS estimated by NREL. And what you can see, I think the kind of point of this study is the cost of producing renewable hydrogen from either curtailment or dedicated on-site renewables is falling pretty dramatically, but that there's a huge amount of uncertainty in terms of where we end up and when it becomes cheaper than SMR or SMR with CCS. So just in terms of what's driving that huge band, so there is uncertainty in the cost of electrolyzers. So depending on the learning curve you assume, we have, you know, an optimistic learning curve on the low end and a conservative on the upper end, which would basically, the conservative has like a 14% learning curve and the optimistic is about a 25% learning curve. Both of which you could compare to the learning curve for solar, for example, has been, I think, around, you know, when we last checked, like low 20%, 22%. That band is also driven by uncertainty in renewable power costs. And then in the, you know, there's also going to be uncertainty basically in terms of the capacity factors that you can achieve. So if you're interested, for example, in why curtailed renewables, it more or less overlaps on-site dedicated solar and wind, but it does look lower at certain points. But, you know, if you're, what you might think is, curtailed renewables, they're free, so why wouldn't they be much cheaper? And what's happening here is that you can get a lower utilization because based on the you know, you don't have curtailed renewables all the time. And so versus a dedicated on-site solar and wind, you can basically operate your electrolyzers at a higher utilization factor. And so you can basically cover the cost on a, you know, per ton of hydrogen basis. You can cover those capital costs, spread those capital costs over more tons of hydrogen. And then I'll just note that for the curtailed power, we're assuming that you could achieve an electrolyzer utilization rate of 15%. I mean, that's still going to be, that's pretty high. And, you know, in reality, some curtailment will be based on local transmission constraints and not system-wide overgeneration. So, you know, you may not be able to achieve as much curtailment as we're showing here. I guess the one other thing I'll note is, you know, you see advanced nuclear, you know, by our assessments based on NREL costs, it's going to be quite a bit cheaper. Quite a bit more expensive just based on those capital costs, despite the much higher capacity factor to use advanced nuclear to produce hydrogen. I will note that, you know, use of the heat generated by the nuclear reactor wasn't included in this cost projection, but that can definitely change the economics. And I think, you know, the punchline should be that, you know, the viability of renewable hydrogen is really going to depend on these capital costs being realized over the next 25, 30 years by the time we hit these mid-century targets. So we did two main analyses that take into, you know, that use those hydrogen costs for the power sector. So we start with E3's Aurora market price forecast. So E3 develops basically scenario-based market prices that reflect different varying assumptions about future policy scenarios in the West. So we used a deep decarbonization price forecast for the West that essentially assumes, as I noted up front, attainment of these different renewable and clean energy targets that are being legislated in the West. So basically assuming a lot of these states are going to hit the 100% renewable or clean energy targets that they had in place. You know, we're using the 2019 price forecast. You know, I'll note that some of these that are 100% sales, that doesn't quite equate to 100% generation. So you still see some gas generation on the system. Of course, if you're going to go to a truly zero gas generation, then, zero, 100% renewable generation, then that would just increase the opportunity for hydrogen. So we take these market gas and we did two analyses. So on the top it says, we did this E3 restore analysis. So restore is basically an optimal storage dispatch model. So given the price forecast that we have and our assumptions around hydrogen's ability to charge in a given hour and discharge, 100 hours later, or basically hold that charge because you can utilize underground storage. We estimated the amount of revenue that it would, 1,000 megawatt hydrogen project would be able to earn in a California market. And we compared that to the levelized costs to give you a sense of kind of what a first mover hydrogen storage project could look like in the market, just in terms of profits. We did a second analysis. So a limitation of analysis on how, the more and more hydrogen you add to the market, you're going to start to impact prices. So here what we did is we built an equilibrium model that as you add hydrogen to the market, we basically restricted this analysis to curtailed power and said, as you add hydrogen storage from curtailed power to the market, you're going to change prices. So, those zero price hours will no longer always be zero price. And as you update this, how much hydrogen could enter the market profitably. And so we came up with, an estimate that I'll show you. It's like in California, I think it's up to 10 gigawatts by 2045. So one other point I wanted to make about the market is that, we focus on the West here right now. The West is dominated by natural gas in California, coal in Arizona, some hydro in the Pacific Northwest. But, given RPS targets and restrictions on natural gas, we anticipate, that lots and lots of renewables are being added to the market, and we're already seeing that. And when we model market conditions in the West, what we find is what we call Dunkelflaut conditions. So these are basically multi-day periods with low renewable output. And so you can see in this simulated day at the bottom where you've got these, yellow is the renewables. They're, charging, or they're over generating in the middle of the day. You're using it to charge storage. That storage is in purple. That storage can then dispatch, battery storage after it's been charged. But when you have these multi-day periods with low renewable output and batteries, we're only adding batteries to the system that are economic. So, you're not getting much above like a 6-hour battery that's cost effective. So you basically run into these multi-day periods where you need some form of, long duration storage or natural gas to fill the gap. Or else, we're ending up in loss of load situations. And this is really that multi-day period is where the hydrogen arbitrage, is profitable.
Please, you have 3 to 5 minutes to
Great.
finish.
Great.
Okay?
Yep. I'm just going to give you a couple more punchlines on the results. So in our first mover hydrogen market model, what we find, if you look at the lower left-hand side, is that you see the costs of a project are falling over time. That's driven by the reductions in the cost of hydrogen storage. And then the revenues are in the blue bars, but based on the year of installation, we're showing every 5 years, these projects start to become profitable around 2030. So the revenues in blue are what those are reflecting is the difference between, the energy discharge revenues minus the grid charging costs, assuming both energy and capacity market revenues from our market model. And we find, so you would think, so CTs are going to be less efficient, but their lower costs are really more than compensating for the lower revenues. And, so we find first mover projects really by the 2030s are quite profitable. We also, I talked a bit about this market model. The kind of punchline of that model is we can find, about 4.5 gigawatts of CTs can enter the market profitably by 2035. So that's, if you compare those blue bars, which are the energy and capacity revenues, to the costs. And then by 2045, up to 10 gigawatts of profitable CTs entering the power market. And so I'm just going to jump right to the takeaway. So, really the takeaway from this study was that, the most promising opportunity for carbon neutral hydrogen we found was as, energy storage in the electricity sector, just given those really aggressive RPS and 100% energy targets. And, our estimate is a market size of around 10 gigawatts in California, and then not shown here, but, around 4 gigawatts in the Pacific Northwest. We did a broader, this was part of a much broader study, as I had mentioned up front. And, we looked at other sectors of the economy and identified, roles in particularly heavy duty ground transportation, where it's possible that hydrogen might play if they can reduce station costs. But I think the hydrogen's role is a bit more uncertain in buildings and industries where there's big structural and infrastructure and barriers. And then I'll note that the kind of, as the production cost figure showed, I think the means of producing carbon neutral hydrogen in the long run remain, really uncertain. And it looks like blue hydrogen, if you have gas with CCS, is cheaper in the 2020s, but that green hydrogen is increasingly looking competitive starting in the 2030s. Thanks. Any questions?
Thank you, Liz. Very, very interesting research. Everybody's talking about hydrogen now, right? And so I was very curious to see your presentation. So we can start to have we have some time for discussion. If there is any question for Liz.
Hi, I actually have a question.
Sure.
Jean-Pierre here. I'm actually quite curious about, well, if you, would you look at using load curtailment and active loads to make not hydrogen, but to get rid of the use of natural gas, for example, or it's not within your models, or something like demand response programs where you give tariff incitations to reduce the load, or
Yep. So we did. So our modeling does assume some role for demand response in the deep decarbonized electricity market. It's just that demand response is really difficult when you get to these like multi-day periods, and really where the hydrogen is making its money is selling in those multi-day periods where you have the low renewable outputs, versus where you can't. I think it's hard to have sustained demand response over 3 days. I think that's a much easier for short durations, at least to some extent, within day, like managed charging, stuff like that.
Yeah. And other sources of flexibility, such as vehicle to grid, for example, these can be very, I mean, from the work I'm doing, these can be very impactful on the investment on distribution network, and I can see their impact on the load profiles. So what I'm asking is that, might these flexibilities affect the profitability of hydrogen, for example, if used on a large scale? Because you can eliminate completely the need for LNG, actually, if you.
Yep. So we do assume basically some vehicle to grid chart. Actually, I don't know. Assume in the study we assume a lot of load flexibility. So something I didn't get into here, but is basically we have a whole different set of models that developed the electrification load forecasts. So I focused a lot on, we have this deep decarbonization price forecast and sort of the supply side of a deeply decarbonized power sector. But also what goes into this modeling is a load forecast and load shapes based on E3's modeling of economy-wide decarbonization in the future. And so, for example, I think something like often 50 to 70% of our EV loads are shiftable to midday. So we have pretty high load shifting capabilities, but yeah, I don't know exactly. Most of that is already baked in.
Okay.
Yeah.
That was it for me. Thank you.
Any other question, please? Okay, Liz, I have two questions. One is more methodological. I would like to understand better, how did you compare the hydrogen as a source of flexibility to the power sector to others sources of flexibility, like the batteries or hydro pump systems? So I'm very, let's say, surprised that the best application is storage for electricity. This is very new as a result, because everybody's talking about using hydrogen for transportation or industry, and you bring something very interesting here. So if you could explain a little bit more about the methodology that you used to get to this conclusion. And the second one is about there is a lot of hydrogen projects pumping up everywhere in the world, and you're showing clearly that they are not economical. So if you can give us a hint of how these projects are being, let's say, subsidized. Who is paying for that, since that they're not economical, sustainable at this point?
Yep. So on your first point about other storage technologies, so the way that this particular modeling was done was that we rely on a price forecast that already did capacity expansion modeling using existing available commercial technologies. So in the West today, for example, you see, I don't know what it is, like less than 10 gigawatts of batteries, right? And that number, so that's the purple here, is huge, order of magnitude, multiple orders of magnitude larger by 2045. So the price forecast that we are using already has baked in a ton of battery build in the region by 2045. We did not, given the scope of this study, include hydrogen in the initial price forecasting. So we are actually working on work that builds it in, basically like build into the optimization. But what we can say is that, storage, what this storage does is it eats up a lot of the available diurnal, curtailment. And so what the curtailment that remains is that multi-day periods where the batteries, have standby losses such that they can't hold a charge for more than, they can't hold a charge essentially for a long period of time and then discharge later. And so it's the multi-day and the seasonal variation where the hydrogen is taking advantage of the opportunities that are left that battery can't take advantage of. I think future work that we're working on now is doing a bit more in terms of kind of horse racing, long duration storage technologies and zero carbon firm technologies against each other. But I think there's just so much uncertainty around, whether advanced nuclear or gas with CS or hydrogen, which one of those wins out is, it's going to be some combination of costs and policy drivers. And it's really almost, I would say it's too hard to know at this point. And I think that any one of those could affect the outlook for hydrogen for sure. Frankly, the emergence of small modular reactors at really attractive costs could change the outlook for hydrogen pretty dramatically, as could not achieving zero carbon, right? Because I think our costs get to like at best around $10 an MMBTU, but I think the AEO forecasts around $5 an MMBTU for gas, so for natural gas. So you really have to have a no gas future to make hydrogen look attractive. To your second question about unprofitable projects, well, I think that's policy drivers for sure, and probably subsidies like site specific costs and contracts. And I think individual project, it will be great to see a project emerge that has really nailed the way to like dramatically reduce costs. I think we know that cheap electrolyzers, underground storage, cheap renewables, those will all help the economics of these projects. But I don't know that I have a strong opinion on sort of like how these projects are going forward, except for some combination of policy drivers and first of their kind investments. I don't know, Anthony, do you have any other thoughts on that? I'll let you give a thumbs up.
No, I think you covered it all.
Okay, so thank you very much. Very, very interesting subject. And yes, we see lots of projects. Everybody's talking about new projects. The project is growing up in terms of size. People are talking about 5 gigawatt projects of hydrogen for export. So I'm very curious to know how this is feasible, and so it was not in your presentation. I knew that this was just a provocation to see if you could give us some light on that. So thank you very much. It was very insightful. If there is no other question for Liz, last chance for the colleagues. If not, I think we can let's go to the end of this session. It was a very, very interesting session where we have seen different scenarios for gas. We saw a scenario where how to end up with gas, how to decommissionate. We saw the importance of the price of carbon for the transition, for deep decarbonization and taking gas out of the energy mix. We also saw the situation in Brazil where we are talking about questions that maybe was important subject 20 years ago in Europe, but still I think that we're gonna live with gas for decades before we reach this decarbonization, and it's much better to have a liberalized, market-oriented gas sector than a monopoly organized gas sector. Even to the decarbonization, I think that decarbonization will happen through market forces, and I think that even if we want to go faster with the decarbonization in Brazil, it's better to set market rules for the market and make it a good environment for new strategies and business models, even to new opportunities like hydrogen. And then we close the session with this very, very interesting presentation on hydrogen, very insightful. I think that I learned a lot. So I thank you all for being in this section and for the question and for the participation. So thank you. And
thank you, Edmar, for chairing the sessions.
Okay, what was my pleasure.
Gonna stop
Okay,
recording.
so